Okay, so last week we left off on this example to, I guess, quickly recap last week what we talked about state space. Uh, State space, reason why we like state space representation. This is our state equation and our output equation. It puts all of our differential equations, like higher order differential equations, into a first order differential equation in matrix form, um, which is very desirable. And basically, when we do that, we define our A, B, C, and D matrices, which will relate to how the states are connected, how the input is connected, and what output we're measuring, and if we see our input in the output. The nice thing about state space representation is that we can use state space to transfer function equation and get the transfer function equation directly from the state space representation. So we so then what we do is then if we want to, let's say, solve for the output, we just take our state space, or not our state, we take our transfer function and then we multiply by the input, and then we take partial fraction expansion to solve for this problem. So one other thing about state space representation is that when we put it into this form, states transfer function representation through state space is not unique. So you can have the same transfer function, but then have different state space representations of it. So this is just one example. Like this is just one state space representation of the system. We can have this. We can have different state space, but represent the same system. And you can prove it through similarity transformations, where you can rotate our states, and it'll still be for the same system. So we're going to go over this example here. So let's say in the case where we have multiple state variables, but of two different systems. So in this case, we have a system with 2 degrees of freedoms. And each degree of freedom, or each system here goes up to the second derivative, will actually have 4 state variables. Okay, so if we look here, we can see that Q double dot and Q1 double dot and Q2 double dot are our highest derivatives for the system. And then on top of that, our output here is Y. It's going to be Q1 plus Q2. So our state variables are going to be Q1, Q1 dot, Q2, and Q2 dot. Notice how our input only pops up for Q double dot. Let me write input there, and then our output here. Okay, if we rewrite this first differential equation, we can rewrite it as Q1 double dot is equal to minus 2Q1 dot minus Q1 plus Q2. That's our first differential equation. Our second differential equation is going to be Q double dot 2 is equal to minus 3 over 2Q2 dot. So I divided both sides by 2 because I want Q double dot by itself. Minus 1/2 Q2 plus 1/2 Q1 plus 1/2 U. All right. So then now I'm going to define my state variables. So what I'm going to do is I'm going to say let x1 equal to q1. So then I want x2 to be equal to q1 dot, x3 equal to q2, and x4 equal to q2 dot. So then with this relationship, we can see that x1 dot is equal to x2, and that x2 dot, or sorry, x3 dot is equal to x4. So then when we plug these variables into our stated equation, or sorry, when we plug these variables into our differential equation, we get the following. So Q1 double dot is just X2 dot right here. So X2 dot is equal to Q1 double dot, which is equal to minus 2x2 minus x1 plus x3. Then x4 dot, which is Q2 double dot, is equal to minus 3 over 2 x4 minus 1/2 x3 plus 1/2 x1 plus 1/2 u. And then our output equation is going to be x1 plus x3. Any questions so far? Okay, so then let's put it in state space form. Maybe I'll go to the right column. Put differential equation in state space form. So then we get x dot, so our x state vector x dot, it's going to be x1, x2 dot, x3 dot, and x4 dot is equal to our A matrix, which we will fill out. X1, X2, X3, X4, plus our B matrix multiplied by our input U. So X1 dot is just equal to X2 from here. This is our first row, first and third row. First row will be our third row. It's going to be on our second row. And this is our fourth row for our A matrix. So it's going to be 0, 1, 0, 0. X2 dot is going to be, so it's minus X1. So it's minus 1. It's going to be minus 2 for X2. It's going to be 1 for X3 and 0 for X4. X3 dot is just 0, 0, 0, 1 because X3 dot is equal to X4. And then the last row is going to be 1/2 for X1, 0 for X2. Let's see, minus 1/2 for X3, and then minus 3/2 for X4. And then for our input only appears in the fourth row as a 1/2. And that is our A and B matrices. And then our output is going to be x1 plus x3. So it's going to be 1, 0, 1, 0 multiplied by x1, x2, x3, x4. And then there's no feed forward input. Maybe I'll just write this. So that's our state space form. Any questions? All right. So that's example where we have 2 degrees of freedom here, where we have 2 different systems with two uh the second derivative for each system here. So therefore we have a we have a 4x4 A matrix because we have 4 state variables. And I think homework problem number 3 is similar to this. You just have to derive the differential equation from the free body diagram first. Okay, so then that's the end of chapter 3 on state space. We're going to jump to chapter 4.10 to 11, which is also related to state space. But now we're going to take this state space here, and then well, actually not this one. We're going to take this state equation here, and then we're going to actually find the time domain solution using the state equation. So this is going to be the time domain solution of a state space, and this is specifically for the natural response. So another effect of putting the dynamics of a system into the state equation is this. Now that we have a first order differential equation, we can actually find the natural solution or the natural response to this state equation because we know the solution to a first order differential equation. So the homogeneous solution to a first order differential equation homogeneous, which implies that our input is 0 and we have initial conditions, instead is this x vector is equal to e to the A matrix multiplied by t times the initial condition vector, and the solution is this. This is the natural response. So this is the natural response. So we're ignoring the force response right now. And then this is where we need to decompose this A matrix to actually find out what this value is. And so the T is your eigenvectors, the matrix containing the eigenvectors of A. So T contains eigenvectors of A. And then your D matrix is your diagonal values of eigenvalues. Have you covered this in 564 by now? No? You just started this morning? Okay. Guess we're still ahead. Okay, so hopefully by the end of this week, after covering this in 564, this will be a little bit easier. But the reason why we like this form is because we like the decomposition is because it makes this solution here feasible to solve by hand. So let me go over this derivation here, where our solution, so x of t, when I write x of t like this, I mean like x1 of t, x2 of t. Our solution for each of the state variable is equal to e to the at times your initial conditions, which is going to be x1 at 0, x2 at 0, time equal to 0, all the way to the x end to the time at equals 0. So this is the solution to specifically just x dot is equal to ax. So maybe x dot of t is equal to ax of t. There's no input. Okay. So if we take the Taylor series, basically what we want to prove is this. We want to prove that e to the at is equal to t e dt times t inverse, where a is equal to t dt inverse. So basically what we want to look at is this. The Taylor series of an exponential. Taylor series of e to the x, for example, is going to be this. 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. And this goes to infinity. So that's the Taylor series of e to the x. So then we can apply this to matrices as well. So then e to the at. So now let's let x equal to at. So then let x is equal to at now. In this case, now x is a matrix. T is still constant. So then that lets e to the at is equal to, so instead of 1, now that's the matrix, it's the identity matrix. Plus x, which is at, plus at squared. So in this case, it's a squared t squared divided by 2 factorial plus a cubed t cubed 3 factorial. And this is also going to go to infinity. All right. So far it's not great if we have to take a to the cubed, a to the fourth, a to the fifth. That's a lot of matrix multiplication. But then what we want to do is then we sub in a is equal to t dt inverse. So then we get this. E to the at is equal to the identity matrix plus t dt inverse multiplied by t plus, when we pull out the 2 factorial. 2 factorial is just 2. 1/2 multiplied by t dt inverse multiplied by t squared. And pull out the 1 over 3 factorial here. And plug that in again. You get t dt inverse multiplied by t dt inverse multiplied by t dt inverse multiplied by t cubed. And that just goes to infinity. So then what's nice about this property is that you can see that these in between T's and T inverses multiply out and become the identity matrix. So then we're left with this equation here. Identity plus T dt inverse T plus 1/2 T d squared T inverse times T squared plus 1/3 factorial of T d cubed T inverse T cubed going to infinity. So it's already simplified this a lot more. We can express the identity matrix as T times T inverse as well here. And then basically I'm going to pull out the T to the left side of this whole equation and T inverse to the out of the right side of this whole equation. I have a different color. So I have T here. Then I get your identity matrix plus dt plus 1/2 d squared T times, or yeah, plus 1/3 factorial d cubed, I'm missing a squared here, d cubed T cubed going to infinity. I'm going to close that parentheses and pull out a T inverse here. And this property here, does it look familiar? Kind of looks like that, right? It's another Taylor series. So we just basically made a simpler Taylor series. We made a e to the dt Taylor series now. So then now we have this. And now we prove that e to the at is equal to t e to the dt t inverse. And what's nice about this property is that d to the n power is equal to lambda 1 to the n power, lambda 2 to the n power, all the way to lambda n to the nth power. Yeah, I'll use a different expression. K power, K power, K power. Change that to a K. And then zeros in the off diagonals. So this property is nice. And when you take an exponential of something that only contains values in the diagonals of a matrix, e to the dt is equal to e to the lambda 1 t, e to the lambda 2 t, all the way down to e to the lambda n t. Because each one of these diagonals is a Taylor series of that corresponding eigenvalue. So then we can plug this expression back into this first line here. Maybe I won't write it out, but basically we can now plug this thing back into the above. And then that is our solution to that is our solution for initial condition response for a system. And all you need to know is the A matrix. And then you can then solve it by hand. Any questions? Okay, so then that's just for the natural response. But let's say we now have the full solution for if we have a non-zero input. In other words, u is not equal to 0, then the time domain solution is this. X of t is equal to e to the at multiplied by your x naught initial conditions plus the integral from 0 to t of e to the a t minus tau times b times u of tau d tau. So tau here is just a placeholder. That's just going to be, we're just integrating up to time t, and you choose time t here. So just to reemphasize this point, this is going to be our natural response. And then this is our forced response, because you can see our forced response is based off of our input. The textbook will redefine it to as a phi of t, which is called the state transition matrix here. And the state transition matrix is also defined as just the inverse of Si minus A. Inverse, but let me check. Oh, the inverse Laplace transform of Si minus A inverse. So that's the state transition matrix according to the book. So this is the full solution. And then basically the where we get our state space to transfer function equation is by taking the Laplace transform of this it's actually taking the Laplace transform of x dot is equal to ax plus bu. And this is the equation when we take the Laplace transform of the state equation. So x of s is equal to Si minus A times x naught plus Si minus A inverse times B times U. And then our output is this equation here. So basically what they did here was they just did this. They did the Laplace transform of x dot is equal to ax plus bu. So then the Laplace transform of x of a derivative is going to be s times x of s minus our x vector at time equal to 0 is equal to a times x of s plus b times u of s. And when we separate everything if we separate the x's, we get s I minus a multiplied by x of s is equal to x naught plus b u of s. Then I take the inverse of Si minus A on the left side to get x of s is equal to Si minus A inverse times x naught plus Si minus A inverse times B times U of S. Now, if I were to plug this into our output equation, y of s is equal to c times Si minus A inverse times x naught plus c multiplied by SI minus A inverse times B times U of S plus D times U of S. Note that this here is our transfer function, highlighted in yellow. Our transfer function, which is equal to Y of S over U of S, is equal to C SI minus A inverse B plus D. That's where the transfer function equation comes from. Oh yeah, no worries. Let's see, it's no, this one's mine. You're good. This one's yours. Yeah. No, we have the same brick. That's why it looks the same. Yeah, no problem. Okay, so that's where our transfer function equation comes from. For those who were dying to find out, I know that probably none of you were, but there you go. That's from chapter 4.10. That's why I included it, because I felt like it's part of state space and that you should see where the solution comes from. So that's the end of this lecture. We're going to start the bulk of chapter 4 next. Are there any questions on state space? Someone raise a hand. Yeah.
Yeah, I have a question. So the Laplace transform state equation that we just went over, I guess there's like probably some relation to the time domain solution.
Yeah.
Did we go over that as well, or no?
No. This is if we were to take let me think about that. So there's a direct proof that will show that this page is equal to this page. I think you have to do it by taking the inverse Laplace transform of this. And when you do that, you're going to somehow show that it's equal to that plus the force response.
Okay.
Yeah.
It's not super important.
No, it's not too important. The main reason why I want to show you this is because I just want to show you that they're both tied to each other. This is the solution to our state equation, or our differential equation in the frequency domain. So we just take the inverse Laplace transform of this here, of these two, then we'll get the time domain solution. But let's say we don't, let's say we're working purely in the time domain, but we do have our ABCD matrices, then we can actually get our direct solution without doing Laplace transform and inverse Laplace transform here. So this skips like taking the Laplace transform plus inverse Laplace transform to finding x of t, if that makes sense. Then the reason why I generally avoid this solution here is just because it's just kind of tedious compared to using transfer function and then multiplying it by the input and taking the inverse Laplace transform. But it's still a valid way of solving it. So I hope that answers your question.
Yeah, that makes sense.
Okay, so then we're gonna start lecture number 4. So lecture 4 is going to be focused on, and hold on a second, let me pull up my notes for it. So pole zeros and system response is mostly centered on chapter 4. I guess like here's the purpose of chapter 4. You're going to learn the difference between a natural response versus forced response, like how to actually solve it. And then you're going to learn how to be able to learn and be able to estimate the system behavior based on the eigenvalues alone. So when I say like learn and estimate, I say like I'll give you the system and then you can just find the eigenvalues only. And then just from knowing the eigenvalues, you can guess if it's going to oscillate, if it's going to be bounded exponential decay, if it's going to be exponential growth, if it's you're going to be able to just tell immediately. So you don't have to solve anything just by looking at the eigenvalues. Um, and then the main purpose, I guess, of this chapter is that this is going to prepare you for future controls courses. Um, the reason why I don't say like outside of class, when you know the poles of a system, that's good, but most systems are nonlinear. So knowing the poles of a system is a very blanket statement. Usually, if you want to guess how a system is going to behave for a nonlinear system, you usually guess it at a local point. So you're going to you're like, I want to know how my system is going to behave just at this point only. You can then guess how it's going to behave. So like if you look at inverted pendulum, we usually linearize it at when it's up vertical because that's where it's the most unstable. And then from there, you can guess how it's going to behave by taking the linearized point at that point, looking at the poles, which is the eigenvalues, and guessing how it's going to behave from that. It's still an important chapter because poles and zeros are the fundamentals of linear systems. And this is in relation to time domain in discrete time, which will be covered in digital controls and 547 as well. You'll learn about the equivalent poles and zeros in the discrete time domain. So we're going to go over some definitions in start of chapter 4, go over first order systems, second order systems in chapter 4.4, and then the last section, which is 4.7, 4.8, is just basically all other systems, meaning higher order systems. If you think about it like this, all higher order systems and linear systems are a summation of first and second order systems. If you take a partial fraction of higher order systems, it just becomes a sum of first and second order systems, meaning that we can approximate all higher order systems as a series of first and second order systems. So we're going to start with chapter 4.1. It's going to be on definitions. And I've mentioned it before, but I keep mentioning it again because it's very important. Your total response of the system is split into the following, which is your forced response and your natural response. I'm going to keep writing this because this is just important. This is your input response, and this is your initial condition response. To quickly inspect a system's response, if it's stable, unstable, oscillating, we look at the values of the poles and zeros. So mainly the poles are what tells us the stability of a system. The zeros tells us slightly less important information, but even knowing some of the values of the zeros can give you an initial guess of how a system's going to behave. More on that later. Knowing the values of the poles is enough to determine stability, and this is in relation to linear systems. And when there is no time delay. So there's actually a case when you have enough time delay, a system does become unstable, even if you have stable poles. We'll talk about that in chapter 10. Okay, so poles, zeros, and systems response. If we let G of S equal to a numerator of S and a denominator of S, so N of S and D of S, basically a pole is defined as values of S that causes the transfer function to become infinity, which is denoted by X, the X symbol. When I say denoted by the X symbol, that means if I were to draw out a graph here and my horizontal axis is the real axis, and vertical axis is the imaginary axis. The reason why is because the S domain is in the real plus imaginary domain. So that's why we have the real imaginary axis. And if I were to draw poles on here, like the location of a pole, that would be my poles. Maybe we have a pole at the origin. These are poles. So basically so we want it's values of s that causes g of s to go to infinity. So in other words, values of s that causes d of s to equal to 0. So let's say if I were to express g of s is equal to, and we don't care what's in the numerator because we're talking about poles here. We have s plus p1. If we factorize d of s, right? S plus p2, s plus, and then we have n poles. Then when g is equal to s, which is equal to minus some pole, ith pole, it's going to equal to infinity. And this is for all I is equal to 1 all the way to n for thoroughness. So then our poles is going to be equal to minus p1 minus p2 minus pn. So those are poles. Poles are our eigenvalues of A as well. Probably have it written somewhere. Maybe I'll write it here anyway. Poles are eigenvalues of A. Our A matrix from our state equation from state space. And this might be a little bit too early, but this is the actual definition in the box here. But there is a case where g of s is equal to infinity. And so the first case is when d of s is equal to 0. What about the second case? What does n of s has to equal to? Infinity. Yeah. So actually, I guess n of s is equal to infinity and d of s is finite. So there is a case where your zeros or n of s contains poles, but we'll talk about that in chapter 8 on root locus. So maybe I'll. But for now, we're just going to focus on values in the denominator that make it 0. Okay. So then zeros are values of s that causes the transfer function to equal to 0, which is denoted by the little circle. So maybe we can say this is a 0. These are zeros. So just values of s that causes n of s to go to 0. And if I were to write that out, usually the way we write it out in the textbook is this: g of s is equal to s plus z1 times s plus z2 all the way to s plus zm divided by d of s. So then our zeros are going to be minus z1 minus z2 all the way to minus zm. And likewise, g of s is equal to 0 in two cases. When n of s is equal to 0, it announced the inverse, or when d of s is equal to infinity. So maybe I'll make a note here that this will be in chapter 8. We'll cover that case. So for now, this case is chapter 4. I'm just writing it down so um I don't make it worse and make you guys make mistakes on the midterm. So to only focus on case one. So it's 11:20. That's the end of lecture. We have I think TA office hours later today. Thank you very much.